All right, in section 2.9, we are going to take a look at inverse functions. So, in order for a function to have an inverse that is also a function, it must be one to one. So, our technical definition of one to one is just each element in the domain is mapped to one element in the range, and also each element in the range is mapped to one element in the domain. Okay, so what that means, this first part was just our definition of a function, right? Each element in the domain is mapped to one element in the range. That means for each input, there's only one output. I can't plug in 2 and get out 7 and then plug in 2 and get out 4. But then also, for it to be one to one, each element in the range is only mapped to one element in the domain. Right? So we looked at something like x squared, where if I plug in -2, I would get 4, and if I plug in 2, I would also get 4. That would not be a one-to-one function. Now, visually, what this means, okay, is that our function passes both the vertical line test, which we use to just determine if it was a function, and the horizontal line test. Okay, meaning if I draw a horizontal line through my function anywhere, it does not touch more than one point. Right? So let's take a look at some examples of that. Right? On your paper, it says which of our parent functions are one-to-one. So here is all of our parent functions with a couple thrown in that we haven't talked about yet. We haven't done logs or exponentials yet, and we didn't do the step function. Okay? But what we're looking at for each of these functions is, do they pass both the horizontal and vertical line test? Okay? Well, the first one, the constant function, is itself a horizontal line. So if I drew a horizontal line through there, I would obviously be hitting more than one point. So this function is not one-to-one. Any line would be one-to-one, okay, because I can draw a horizontal line anywhere and not hit more than one point. The absolute value function would not be, because I can draw a horizontal line and hit multiple points. Okay, this would not be a one-to-one function. Same idea with the quadratic. If I draw a horizontal line, I can hit more than one point. The square root function would be, and again, same reasoning. If I draw a horizontal line, I'm only going to hit one point anywhere. The parent cubic function would be one-to-one. The cube root function would be one-to-one. The reciprocal function, or the inverse, the 1 over x function, would be. But 1 over x squared would not be, because if I draw my horizontal line, I would hit more than one point. Right? Now, again, we'll talk about these two types of functions in a later chapter, but just looking at the graph, I can see that a logarithmic function is one-to-one and an exponential function is one-to-one. But a step function, and again, we didn't really talk much about these, okay, but a step function would not be one-to-one, because if I draw horizontal lines, I can see that I'm going to hit multiple points through that horizontal line. Right? So that's the idea graphically. Now, if we are just given functions, like in this next example, we still kind of want to think about what these would look like on a graph. And because we talked so much about transformations of functions, I do expect you to be able to visualize what each of these would look like. So this absolute value of x minus 3, if we can just sketch a quick graph, well, that's the absolute value function shifted right 3. So that would look something like that. Okay, and again, when you're visualizing for this purpose, it doesn't have to be exact, right? We just want to see what's happening. So this would not pass the horizontal line test. So this function is not one-to-one. The line 2x plus 5, well, we've got a y-intercept of 5, a slope of 2, so that's going to look something like that. That would be one-to-one. does pass the horizontal line test. This one, x squared minus 1, is our x squared function shifted down 1. Right? So something like that. That would not be 1-to-1. And last, 2 times the square root of x is just going to be our square root function vertically stretched by a factor of 2. So it would look something like that. So this one is 1-to-1. It passes the horizontal line test. I can draw a horizontal line anywhere and not hit more than 1 point. Okay? So let's then start talking about inverse functions. So if our original function is f of x, we denote the inverse like this. Okay? Now, we want to be careful. This does not mean to the negative first power. Right? This means the inverse. Right? Taking the negative first power can be different sometimes. So the big takeaway for an inverse function, okay, a function and its inverse undo each other. Okay, they undo each other. They cancel each other out. Just like, simple inverse operations like addition and subtraction undo each other. They're inverse operations. Multiplication and division undo each other. Right? Later on, we'll talk about logs and exponentials undo each other. They're inverse operations. So in terms of notation, what we're saying is if I compose those functions, if I take f inverse of f of x, or the other way around, f of the f inverse, that's going to cancel everything out, and it's just going to equal x. So a couple of simple numerical examples of that idea. If I know that f of 4 equals 7, so what that's saying is the point 47 is on my original graph, well, then I can say that the point 74 is on the inverse. Right? If my functions undo each other, these opposite points are going to be on the graph. Same thing here. If the point 5, negative 2 is on the inverse, then the point negative 2, 5 will be on my original graph. Right? Now, this one lets us see that same idea. Let's say our original function is x cubed. Well, if I plug 2 into that, I would have 2 cubed, right? And 2 cubed is 8. Well, then I want to find f inverse of 8. Okay, so again, if we found that f of 2 equals 8, the opposite's not the right word. If I switch x and y here, that point would be on the inverse. So f of 8 would equal 2. Now these last two, f of f inverse, remember this notation just means f of f inverse like this. So we just said that a function composed with its inverse undo each other. They cancel everything out. So this would be just equal to 15, right? Up here we said they cancel each other out and we're just left with x. Well, in this case, we're plugging in a value. So that would just be 15. Same idea here. F inverse of f is just like this, and this time we're plugging 27 into that. So these undo each other. They cancel each other out, and that's just equal to 27. Right? So the next example, we get into a little bit of algebra. So we're given two functions. F of x equals the cubed root of x plus 1, and g of x equals x minus 1 cubed. It says show that these are inverse functions. So we're told these are inverses and just asked to prove that. To prove that, what we're going to do is find the composition f of g of x and the composition g of f of x. And if both of those work out to just equal x, then these are inverses of each other. Right? If these functions undo each other and we just get x, then they're inverses. So let's find f of g of x. So that means I'm taking g of x and plugging it in place of x over here. So I'll have the cubed root of x minus 1 cubed. Right, I'm just plugging this whole thing in place of x plus 1. So the cubed root and the cube cancel each other out, and I would just have x minus 1 then plus 1. So negative 1 plus 1 cancels out, and I'm just left with x. Now we have to find the composition in the other direction as well. I have to find g of f of x and show that both of these compositions equal x to prove that these are inverses of each other. So in this case, I'm going to take this function and plug it in place of x here. So I'm going to have the cubed root of x plus 1 minus 1 cubed. Well, plus 1 minus 1 cancels out, so I just have the cubed root of x cubed, and the cube root and the cube cancel out, and we get x. So since I was able to show that f of g of x equals x and g of f of x equals x, that proves that these two functions are inverses of each other. Right? So this first bullet point down here, we kind of already alluded to this, but it says if AB is on f of x, then the point BA is on the inverse. Right? All I'm doing is switching the x and the y coordinates for a function and its inverse. Okay? And let's explore that idea a little bit more here. So graphically, what that means is that a function and its inverse are symmetric about the line y equals x. Right? So in both of these examples, we are given a function and we want to sketch the inverse. So what I'm going to do first is draw in y equals x. Let's see if I can make that look straight here. It looks pretty good. Right, y equals x. So in order to, I'll go ahead and draw it over here as well. In order to reflect something across the line y equals x, what we are doing is just switching every x and y ordered pair. So in the previous bullet point, we said if AB is on F, then BA is on F inverse. So this point here on my original function is -2, 0. That means that the point 0, -2 will be on my inverse function. Okay. Then I've got the point -1, 1. So the point 1, -1 will be on the inverse. Right? Then way over here, I've got the point 2, 2. Well, if I switch those coordinates, I'm still at 2, 2. And we can start to see what this is going to look like. All right, so here is what my inverse would look like of the square root of x plus 2. Okay, it is a reflection across the line y equals x. So we can, kind of visualize if I fold this in half, these would sit on top of each other. What we're literally doing, though, okay, is just taking each coordinate point and flipping the x and the y. Right? If it's reflecting across y equals x, I'm literally just switching the x's and the y's for every coordinate point. Right? So let's do another example here. So let's say our original function is just, we've got the points -3, -5, -1, 2, and 4, 3. So it's just, we're connecting those points. So there's my function. And I want to reflect this across the line y equals x. Well, all we're doing is taking each coordinate point and switching x and y. So for the inverse, the point -5, -3 will be on the graph. So -5, -3 is right there. And the point 2, -1, so 2, -1, and the point 3, 4. Right? So here is my inverse. A couple of things to notice and make sure that you're sketching your inverse correctly. Wherever our original function crosses the line y equals x, our inverse should also cross the line y equals x at that point, right? Another way to look at this graphically is that the distance from each point to the line y equals x should be exactly the same as the distance from the inverse. Okay, so here we can see that those distances to those points are exactly the same. Same here. Those distances are exactly the same. All right, so a function and its inverse are just reflected across the line y equals x. Let's take a look at how to find an inverse algebraically now. So 4 steps. First, just replace f of x with y. Right? Usually we're given a function as f of x equals something. Then switch all the x's and the y's. If there are multiple x's, replace them all with y. Then solve that new equation for y. Get y by itself, and then replace y with this notation for the inverse, okay? F inverse of x. So let's go through a couple of examples here. Let's say that we first want to find the inverse of 2x plus 3. So we want to find the function that undoes this function. Well, let's go through our steps. So it says replace f of x with y. So y equals 2x plus 3. Then switch all the x's and the y's. So then I'll have x equals 2y plus 3. Right? I'm not doing any operations. All I'm doing in that step is replacing any x's with a y and replacing any y's with an x. So now I want to solve this new equation for y. So I'm going to subtract 3 over and divide by 2. So I'll have x minus 3 all over 2 equals y. And then the final step is to replace y with this notation. So I'm going to say f inverse of x equals x minus 3 over 2. So this function is the inverse of my original function. All right? Then it just says, use Desmos to check our answer. So I went ahead and plugged both of those into Desmos, and along with the line y equals x here. And we can see that they are reflections of each other across the line y equals x. All right? In our next example, we've got x squared minus 1. So let's go through these steps. Okay, replace f of x with y. So y equals x squared minus 1. Switch all the x's and the y's. So I'm going to have x equals y squared minus 1. Then solve this new equation for y. So add the 1 over and take the square root of both sides. Now when I take the square root, I'm going to have plus or minus. Okay, so this is my inverse. Now, I do want to point out here that if we think about our original function, x squared minus 1, that's a quadratic, it's a parabola, it is not 1-to-1. That means that the inverse is not a function. we were still able to find the inverse, but we have the plus or minus, right? So the inverse is not a function, right? So even if our original function is not one-to-one, we can still find an inverse. It just is not a function. So visually, this is what that looks like. All right, here's my original parabola, the blue one here, the line y equals x, and then I had to type in two different pieces for the inverse, the positive square root of x plus 1 and the negative square root of x plus 1. And we can see that those functions are reflections of each other across the line y equals x. One more example. All right, so here, again, let's go through our steps. So we're going to have y equals x plus 2 over x plus 1. Then switch all the x's and the y's. So I'm going to have x equals y plus 2 over y plus 1. In this case, we have two x's in the original function. So when I switch that, I'm going to have two y's. To solve something like this, the first thing I want to do is get rid of the denominator. So to do that, I'm going to multiply both sides by that denominator, by y plus 1. Over here, those are just going to cancel out. And over here, I'm actually going to do this distribution. Okay, I'm going to have xy plus x times 1 is just x equals y plus 2. So now, whenever we have a situation like this where we have multiple y's, what I want to do is get all of the terms with a y on one side of the equation and then get everything else on the other side of the equation. So I'm going to, and it doesn't matter which side we subtract things to, but how about we move this y over to this side and we'll move this x over to this side. So when I do that, I'm subtracting this y over here. So I'm going to have xy minus y equals, and then I'm going to subtract this x over to this side. So I'll just have 2 minus x over here. Let me continue up here. So now the reason that we do that is I can now factor a y out of everything on the left. When I do that, I'll be left with x minus 1. Okay, so this left side of the equation would turn into this. And then I would still have equals 2 minus x. Then, to get y by itself, I can just divide both sides by x minus 1. And I'll be left with y equals 2 minus x over x minus 1. And then the final step, replace y with f inverse. So the inverse of my original function is 2 minus x over x minus 1. So this function would undo this function. And again, if we look at those, okay, we can see that they are actually reflections of each other across the line y equals x. And we haven't really talked about graphing rational functions yet. We will in a later chapter, right? But this is what those would look like. Okay, the blue one is my original function, and the red one is my inverse. Right? So that's it for this video. The final question is going to pop up, asking you what questions you still have.